So if I look at the periodic table, it gives me the masses of atoms of an element. If I look at them, they're not integers very often. I get, for example, for lithium, 6.94, definitely not an integer. And that's because what it's showing you here on the periodic table is the average mass for all the isotopes of that element. So if lithium has some isotopes that are heavier than 7 and lighter than 7, you're going to have the average showing there. Now, if I go and look at the actual isotopes for lithium, here are the abundances and the isotope masses for both of those things. How can I figure out the average mass from this information? Well, it turns out that this weight that you have on the periodic table is just a weighted average of these two things. What does that mean? It means that if it was a 50-50 mixture of lithium-6 and lithium-7, you could average these two, and that would be the weight that you'd see on the table. But it is not a 50-50 mixture. It's a 92.41 to 7.59 mixture. So how do you take the abundances into account when you're trying to calculate your average? The average mass is going to be equal to the abundance of the first isotope times the mass of the first isotope plus the abundance of the second isotope times the mass of the second one. Now, I'm going to put a box around this, and you should know by now when I put a box around something, that's worth memorizing for the test. This will allow me to take all this information and compute an average from it. So let's do it. Now, I'm going to put the abundance in. Remember what I said about abundances. You want to not use the percentage abundance. You want to use the actual decimal number for this. So if it's 7%, you can turn it into a decimal number by bumping the decimal place back 2 places. So abundance 1 should be written down like this. So I wrote down 7.59% this way. That's abundance 1. Mass 1 is this. Plus abundance 2. I'm not going to write down 92.41. I'm going to write down 0.9241 because I bumped the decimal place over 2 places to get rid of the percent sign. And here's the mass of that isotope. And now all I got to do is grind it out on the calculator. Oops, got to turn the calculator on first. Plus 0.9241 times 7.0160 gives me 6.9400. Now, how many significant digits should I have? Well, if I look at this first one, there's 3 significant digits times something with 5. So this product is going to have 3 significant digits. What was it again? Let's take a look. So when I did this product, this times this, I get 0.4565 whatever. But there's only 3 significant digits here, so how far out does that go? It goes out to the thousandths place. And that's kind of the weak link here. It's going to be a weaker link than this one, so I don't even have to check that one. I can go out to the thousandths place, so I can cut it right there, and I can write my average as that. Now, let's compare that to what we have in the periodic table. This table has got things rounded down pretty bad, but that's 6.94, so I hit it straight on. In other words, my abundances and my mass are consistent with what's on the table. Well, why wouldn't they be? Because sometimes the abundances vary depending on the source of the material. If you've got lithium from Earth, it's got this set of abundances maybe, and that might only be in one part of the Earth. If you go to another part of the Earth, these might be slightly different. So these abundances give you a way to trace materials. In fact, they're used a lot in forensics. You can take isotope abundances from different places and tell where something came from. You can tell where somebody's been living for a while by the isotope abundances of the hydrogen in the water in their body. So these abundances are important in tracing materials in various different problems.